Mr. LaBeouf here with the first instructional video for the 2020-2021 school year for St. John's 7th grade pre-algebra students. And the topic of this video is integer operations. Eventually we'll have to take any two rational numbers, and as we've talked about in class, a rational number is a fraction or a negative fraction. The integers are rational numbers. They are special kinds of rational numbers. The technique that I urge you to use is this. When you've mastered integer operations and then you approach non-integers, you will approach them the same way in terms of the sign. Of course, you'll also have to remember everything you've learned about fraction or decimal operations in 5th and 6th grade, and then just put on top of that the rules for signs that you learn with integers. So it's a sort of a bringing together of those two sets of skills. But today we're just going to focus on the integers. We're going to add, subtract, multiply, and divide any two integers. Now, to begin with addition, we're going to consider vectors on the number line. We are eventually going to develop rules that we can state and apply abstractly to just the numbers as we see them, without reference to the number line. But to really cement this knowledge and understanding, we're going to see how integer addition can be explained with vectors on the number line. So let me get that set up. We're going to begin by looking at the integer addition 2 plus 5. 2 plus 5. The positive 2 is represented by this vector that begins at 0. It has a beginning point at 0, and the arrow is the end point, which is at positive 2. And the whole number 5 is represented by a beginning point at 0 and an end point with the arrow at 5. These vectors are added by placing end point on top of beginning point, or beginning point on top of end point. So if we take the beginning point of the 2 and place it right on top of the end point of the 5, it would look like this. I didn't use a ruler there, so it's a little shaky, but what I've done is I've translated or moved this vector so that it is its beginning point is at the end point here, and of course it goes 2 units further to the right and ends up at 7. 5 plus 2. Pretty straightforward. But the important thing is to see that the next problem that I'm going to do works in a very similar way. For emphasis, I've made these two vectors red, but the important thing is not so much the color, but the fact that they point to the left. Those vectors represent negative 5 and negative 2. Negative 5 has a beginning point at 0, points to the left, and its arrow ends up at negative 5. Negative 2 starts at 0. The end point, which is the arrow, is at negative 2. And I'm going to add these two vectors the exact same way as before, putting end point on beginning point or beginning point on end point. So I will take this negative 2 and bring its beginning point here to the end point of the negative 5, and it's going to extend, of course. It's going to have the same length as it did here. It's the same vector, it's just been moved, and so it ends up at negative 7. That becomes the answer. What we just did was negative 5 plus negative 2, and it ended up at negative 7, in the same way that 5 plus 2 ended up at positive 7. Addition is commutative. And I chose to move this vector up here, but I just as easily could have moved the other vector. I could have taken the vector representing negative 5 and put it here. It put its beginning point there, and then of course it extends 5 units to the left and ends up at the same -7. So 5 plus 2 is 7, and -5 plus -2 is -7. And this leads us to our first rule that we can state abstractly and be able to handle these additions without reference to the number line. When you're adding two numbers with the same signs, you take their absolute values and add them, the way you did as a very young student. But then, the sum is going to have the same sign that the original two numbers had. So the absolute value of 5 is 5, the absolute value of 2 is 2. To do 5 plus 2, you do 5 plus 2. It's +7 because the 5 and the 2 were each positive. To do -5 plus -2, you also mentally do 5 plus 2. You take the absolute values of each number. The absolute value of -5 is 5. The absolute value of -2 is 2. You add those to get 7, but then you recognize that each of the numbers was negative, so the answer is negative. And you saw how it worked with the vectors. 5 to the left and 2 more to the left. The fact that these vectors went end to end and got longer, that goes along with the fact that you're adding the absolute values. So this is the rule for adding two numbers when the signs are the same. Now we're going to look at the rule for adding two numbers when the sign is different, when the signs are different. We're now going to look at 5 plus -2. You might know by now, you should, that 5 plus -2 is equivalent to 5 minus 2. So the answer here is going to be 3. But we're going to look at it in terms of movement of vectors. The +5 is a vector pointing to the right that starts at 0 and ends at 5. The -2 is a vector that starts at 0, points to the left, and ends at -2. Remember the rule for adding the vectors. End point to beginning point to end point. Either way, addition is commutative. It doesn't matter which one you move. Let me move this one so that the beginning point of the -2 is now moved to the end point of the 5, and then it, of course, comes back to the left by 2 units, and bam, it ends up at the answer, which is +3. Maybe that should be in black since it's positive. If I had taken the vector representing 5 and moved it here so that its beginning point was here, at the end point of the -2, it would have come back 5 units to the right and also landed on 3. See if you can guess what the final problem was going to be. The final problem is -5 plus 2. This time, -5, we have a vector beginning at 0 pointing to the left 5 units, and the +2 beginning at 0 and pointing 2 units to the right. And when we move beginning point to end point, let's take 2, the +2, and move it so that its beginning point here falls on top of the end point of the -5. It's going to come back by 2 units to the right. It's the same vector as here, it's just been moved over, and of course look where it lands. It lands at -3. So let's state the rule now for adding two numbers with different signs. You take their absolute values and subtract the way a first grader does. So in each of these cases, you're going to do 5 minus 2, right? The absolute value of 5, the absolute value of -2, 5 and 2, and you subtract 5 minus 2, and you get 3. Now, for 5 plus -2, the answer is 3. Why? Because the number with the higher absolute value is positive. The number that's further away from 0 is positive, so the answer is positive. With the other one, you're adding numbers with two different signs, a negative plus a positive. So you're going to take the two absolute values and subtract. Here you're still going to do mentally 5 minus 2. But you're then going to recognize that the number that's further away from 0 is negative, so the answer is negative. And you can see that visually with the vectors. You see the -5 stretched all the way to here. And when you put the positive 2 vector here, when you move it over where it needs to go at the endpoint of the negative 5, it's going to come back, but it's not going to reach 0 because the negative 5 was further away from 0 than the 2 was. So it's only going to reach to negative 3. And another thing, to understand the subtraction, you can see that a certain length gets canceled out. Because the vectors point in different directions, when you place beginning to end point, rather than adding lengths like we did with 5 plus 2 and negative 5 plus negative 2, there we added lengths. Here the length is getting shorter because of this overlapping of the left pointing and the right pointing. So that's addition. We're going to move on next to subtraction, but in order to subtract, we're going to operate by a definition. And once we establish the definition for subtraction, we fall back on the rules for addition. So here's the rule for subtraction. What is subtraction? Very simply, subtraction is the addition of an opposite. To subtract a number, add its opposite. Let's take a look. We've already looked at 5 plus negative 2, right? Didn't we just do 5 plus negative 2? Well, first graders never see that. They see it as 5 minus 2. Okay, so if we start with, let's start with the 5 minus 2 that we all know from our very early years of math. We are subtracting 2. That is the same as adding the, subtracting 2 is the same as adding the opposite of 2, which is negative 2. Subtracting 2 is adding the opposite of the 2, which is negative 2. So either way you look at it, the answer is 3. But what about if you have a negative number and then minus? What if you have a situation like, let's say, negative 5 minus 2? What if you have negative 5 minus 2? Well, we've got a number here. We've got negative 5, and then we're subtracting 2. See, the minus sign, this horizontal line segment that goes in front of a number, it can be thought of in different ways. To a very young person, it's take away. And then we start to call it minus or subtraction, or we call it the difference between two numbers. It indicates subtraction, but it also indicates opposite of, right? And you have to be comfortable with the fact that it has these various interpretations. Here, I'd like you to see this as the number negative 5 and then minus 2. Okay? Subtracting 2 is the same as adding the opposite of 2, just like it was in the previous example. That doesn't change just because this is a negative 5. So what you actually see here is this subtraction is an addition that we already did, right? This is the addition, negative 5 plus negative 2. To subtract 2, you add the opposite of 2, which is negative 2. So the answer there is negative 7. This takes a little getting used to sometimes. Sometimes students will not recognize that these two have the same answer. They have to have the same answer because they are what we call equivalent. They say the same thing by the definition of subtraction. Now we come to the weird kind of subtraction, but it's not really weird if you remember the definition. Sometimes we have to be able to handle the subtraction of a negative, but the way I've defined subtraction, this really isn't any different, because if you recall, I defined subtraction and I was very careful with the words I chose. To subtract a number, you add its opposite. And I intentionally stayed away from the word negative there, because opposite is really what we want. So look at that first one, 5 minus negative 2. I'm going to see this as the subtraction, this first minus sign. And then I'm going to see after that negative 2, minus negative 2. I'm subtracting negative 2. To subtract a number, you add its opposite. So to subtract negative 2, you add the opposite of negative 2. So this becomes, believe it or not, 5 plus 2. 5 minus negative 2 is exactly equivalent to 5 plus 2 because of the definition of subtraction. The addition of an opposite. Not the addition necessarily of a negative, but the addition of an opposite. This one here is really no different in how we approach it. It has a different answer because the first number is different, but it's approached the same way. Negative 5 minus negative 2. To subtract negative 2, you add the opposite of negative 2. So you end up with negative 5 plus the opposite of negative 2, which is 2. So you have negative 5 plus 2, which is negative 3. Now, we saw both of those earlier. We started with 5 plus 2. Now we see that it's equivalent to this. And then we also did negative 5 plus 2 at one point, and we see that it is equivalent to that. So, ladies and gentlemen, this is addition and subtraction. It's a little bit quick, but you've seen this before. There is something that I would really love to do now, but I want to keep this video with a reasonable amount of time, and we have to still talk about multiplication and division. I would love to talk about the fact that when you subtract two numbers, if the bigger number is first, you're going to get the distance between the two numbers on the number line. And if you don't put the bigger number first, if you do smaller number minus bigger number, you're going to get the opposite of that distance, the negative or the opposite of the distance on the number line. I'm going to try to remember to do a separate video about that because I think that's a really cool topic to help people to really relate more to subtraction. When you see that subtraction can answer a very important question, very obvious question of what is the distance between two numbers on the number line. So that will come, but right now we're going to move on to multiplication and division. Here's some good news about multiplication and division. It's easy. The rule for multiplication and division is the same as far as the signs go, and that rule is easy to state. If you're multiplying or dividing any two numbers, if the signs are the same, the answer is positive. And if the signs are different, the answer is negative. See how simple that is? Addition is a little bit more complex to state the rules. I'd like to repeat the rules for addition. Back to addition for a moment. When you're adding two numbers, if they have the same signs, positive plus positive or negative plus negative, you add the absolute values, and then the answer will have the same the same sign that the two numbers have. So 5 plus 2 was 7. Negative 5 plus negative 2, negative 7. You add the absolute values and then go with the sign that the two numbers have when the signs are the same. But when you're adding two numbers with different signs, you have to take the absolute values and subtract, the way a first grader would. And then the sum will have the same sign as the number with the higher absolute value. So 5 plus negative 2, you do 5 minus 2, and the answer is positive 3 because the 5 was positive, and that was further away from 0 than the negative 2. But if you do negative 5 plus 2, different signs, you're still going to subtract, but this time the answer will be negative 3 because the negative 5 was further away from 0 than the 2. So I went back and restated those rules for addition because just to sort of contrast them with multiplication and division. Just think of all the wording I had to use there, and I hope I did it correctly, by the way. You got to be careful, it's so wordy. But with multiplication and division, you're multiplying or dividing two numbers. If the signs are the same, the answer is positive. If the signs are different, the answer is negative. Let's explore why that's true. We're going to use something Hi there. No. I've written something on the board that I have proven to you, and I've decided not to include the proof here in this video, again, for time limitation purposes. Maybe on a separate video I will record for you so that you can refer back to it if you like, why this statement is true. But you can trust me that it is. If you multiply any number by -1, -1 times a number is the opposite of the number. And it is important to see here that to read this as the opposite of x, the opposite of the number. Here this negative sign is serving as meaning the opposite of. Okay? -1 times a number is the opposite of a number. And that works for any x. -1 times 3, here the x is 3. So the answer is the opposite of 3, which is -3. But if the x is -3, the x could be -3. And then you have -1 times -3. And the definition, I'm sorry, it's not a definition. It's actually a theory that we prove. This theorem, -1 times x equals the opposite of x. There's a proof for it. So it's a theorem. It's official. We can use it. It tells us that -1 times -3 is the opposite of -3. See, the number is -3. So -1 times that number is the opposite of the number. And the opposite of -3 is 3. Now, if you look at these two, you can kind of see the rule for multiplication right there. When the signs were different, negative times positive. When the signs were different, the answer was negative. But when the signs were the same, negative times negative, the answer was positive. It's one of the big issues in middle school math. One of the biggies. If adults, years later, they think back on middle school and high school math. And one of the things that they might recall is a negative times a negative is a positive. That's a strange thing. If it seems strange to you, it should, because it is. It is really this theorem that multiplying any number by -1 gives you the opposite, which proves that a negative times a negative is a positive. But again, we'll not include that proof here. On the left, we have the same sign problems, and on the right, we have the different sign problems. When you're multiplying or dividing, when the signs are the same, the answer is positive. So here they're both positive, so the answer is 12. Here they're both negative, so the answer is also 12. Now, let's explore that just a little bit. We're not proving in this video that -1 times a number is the opposite of a number, but let's use it right now to explore this a little bit. -3 can be written as -1 times 3, right? When you multiply a number by -1, you get its opposite. So -1 times 3 is the opposite of 3, which is -3. And this -4 can be thought of as -1 times 4. Right? -1 times 4 is the opposite of 4, which is -4. The associative and commutative properties of multiplication allow us to multiply a bunch of numbers in any way that we want. So how about if we do this? -1 times -1 times 3 times 4. When you multiply a number by -1, you get its opposite. So look at this. I'm multiplying, let's say I'm multiplying this -1 by -1. So I'm going to get the opposite of this -1, which is 1. There's a very similar proof of the fact that -1 times -1 is 1. The proof works very similarly to the proof about -1 times x equals the opposite of x. It's a very similar proof. And both of those proofs are very short. And I will include them in a separate video if I remember. But let's just accept this for now. Multiplying this -1 by -1 means we're going to get the opposite of this -1, which is 1. So these two multiply to 1. And again, that's the rule when the signs are the same. You see, but I'm kind of, you see, I can't really say at this point, I really have to prove to you that -1 times -1 is 1. Because otherwise we're just using the rule here and to try to explain why it works here, and that's not valid. At some point you have to prove that -1 times -1 is 1, and I can and will do that for you. But once we do that, once we prove that -1 times -1 is 1, then we can take any situation where there's a negative number and pull that -1 out, and like we did here to do -3 times -4. So this is 1, and that's 12, and 1 times 12 is 12. The other two, on the other side, the signs are different. One is positive, one is negative. The rule says that the answer is negative. So this is -12, and this is -12. Either way, as long as the signs are different. That business of -1 times a number giving you its opposite, well, we can use that here. -1 times 3, and then we have times the 4. -1 times 3 is the opposite of 3, which is -3. So we can represent -3 as -1 times 3. Then we can do this. 3 times 4 is 12, and then we have -1 times 12. And once again, -1 times 12 is the opposite of 12, which is -12. You don't have to do all of this. See, my explanation of why things work are designed to get you to believe and to really buy into the program, to make it have tremendous meaning for you. But you don't have to, all you have to do is remember that when you're multiplying two numbers and the signs are different, the answer is negative. And when you're multiplying two numbers and the signs are the same, the answer is positive. Very simple. But these whys, I hope, are going to be valuable for you, the why of it. And here, of course, we can represent the -4 as -1 times 4. We can multiply them in any order we want, so we can see it as -1 times 3 times 4. This is 12, and -1 times 12 is -12. Let's look at division. This is a very similar setup to what we did with multiplication. On the left side, I have the two situations where the signs are the same, and on the right side, I have the two situations where the signs are different. When you're multiplying or dividing two numbers, when the signs are the same, the answer is positive, and when the signs are different, the answer is negative. 12 divided by 3 is, of course, 4, but so is -12 divided by -3. That is also 4. Over on the other side, the signs are different. 12 divided by 3 is -4. So is -12 divided by 3, also -4. So I could close it there. But what I'm going to do for you now is to show that these rules, these two rules for division, are consistent with the two rules for multiplication. And that has to do with the definition of division. We have to take a little trip back. I know I've taught you this in the past. What is division? A division is a question about multiplication. Why is 12 divided by 3 4? Well, it's because 4 times 3 equals 12. This is a very important thing to go through with fraction division. When you're developing the rule for keeping the first fraction, when you're dividing two fractions, flip, keep the first fraction, change the division to a multiplication, and then flip the second fraction. I would hate to have to just tell my students, that's the way it is, do it. So instead, I always explain why. And to explain why you flip that second fraction and multiply, you have to go back to the definition of division, that a division is a question about multiplication. So that's for another time, why we flip a fraction and multiply. But the reason that 12 divided by 3 is 4 is because 4 times 3 is 12. Now look at this one. Why is this true? Why is the answer here 4? Well, according to the definition of division, see, a division is always a question about multiplication. What we're searching for here is a number that you can multiply -3 by to get -12. The quotient of the division, the answer to the division, you must be able to multiply that by the bottom number to get the top number. So we will now write because 4 times -3 equals -12. You see what I mean by we can use the rules for multiplication to derive the rules for division. Okay? We know that 4 times -3 is -12, so the 4 works here. Right? The 4 is the number that you multiply -3 by to get -12. Over here, why is 12 divided by -3 -4? Because -4 times -3 equals 12. All right? And the very last one here, why is -12 divided by 3 -4? Because -4 times 3 equals -12. Everything fits together. Everything is consistent. You've learned the rules for multiplication, and you state the rule for division the same way. But not only that, but you can then look at the definition of division and asking, you know, why is this the quotient? Why? Why are each of those the quotients? And then you can answer that question by going back to the rules for multiplication. So I think I'll draw it to a close there. There are other things that I could talk about and that I will try to remember to talk about in the future. But this gives you a review. I'm hoping that all of you have seen this before, but you will realize how important it is to really master this. I'll give you opportunities to practice, continuing to do that, but be aware that we'll have to move on to adding, subtracting, multiplying, and dividing any two rational numbers, not just the integers, but also fractions and negative fractions. The good news is that the rules for signs will not change. You will approach the question of what sign does the answer have? How do I get to the answer in terms of the sign? You will answer that question the same way for the rational numbers that you did with the integers. But then, of course, on top of that question about the signs, you'll have to also remember how to do the calculations with fractions and decimals. So enjoy your weekend. We've already seen in class that these skills of integer operations and later on the rational number operations are not going to be learned just for themselves, but they'll be applied. They are learned so that we can solve equations, which is the heart of algebra. Take care. 7th grade pre-algebra students, I'll see you soon. Bye-bye.